As we discussed for delta S naught for the universe, or the change in entropy of the universe, many reactions are product favored at some temperatures and reactant favored at others. This occurs when one of the terms in the Gibbs free energy equation is favorable and the other is unfavorable. We're now going to look in more detail at these types of reactions to understand why this is. Let's take the example of the freezing of water at 1 atmosphere. That's when water as a liquid turns into water as a solid. Now delta H fusion will be negative because energy is released as the bonds are formed. Delta S is also negative. The disorder decreases as the crystal forms. You went from a solid to a liquid. So we have our Gibbs free energy here. At what temperatures will this reaction be thermodynamically favorable? To be thermodynamically favorable, delta G has to be negative. That's how we defined it. So the phase change will occur at low temperatures. The reason for that is the term negative T delta S has a positive value, and this is minimized at low temperatures. Let's look at the combustion of gasoline, which is the C8H18, or another name for that is octane, and it's combustion because you're burning it with oxygen, at 1 atmosphere. Delta H is negative because energy is released as new bonds are formed, and delta S, the change in entropy, will be positive because you've increased the number of moles of gas products. That doesn't always work, but in this case it does. And here we have 2 moles of gas plus 25, so that's 27. Your products, there's 16 plus 18, that's 34. So that's an indicator that entropy goes up. At what temperatures will this reaction be thermodynamically favorable? Well, let's look at our Gibbs free energy. Delta H is always negative, okay? Negative T delta S, well, what's that? Delta S is positive, so negative times a positive will be negative. So I have 2 negative numbers here. You add them together, we're going to get a negative value for Gibbs free energy, so the reaction is favorable no matter what the temperature is. Example number 3, photosynthesis, basis for life on Earth here, right? Carbon dioxide plus water yields oxygen and sugars. Delta H is positive since energy is absorbed to create new bonds. Change in entropy will be negative since many moles of gas are converted to fewer moles of gas. Well, let's just check that. We have 6 plus 6, that's 12. And on the right side, we just have 6 moles of gas. So at what temperatures will this reaction be thermodynamically favorable? We'll take a second before I move the answer, so you can pause the video if you'd like. And now we're going to move the answer away, or the cover of the answer. And what do we see? The reaction is unfavorable at all temperatures, as both the enthalpy and the entropy terms are positive. So what do we mean by that? Well, delta H over here, that's positive. Now we said delta S is negative, okay, but we're multiplying it by negative T, negative times a negative, positive. So that's what we mean. There's your enthalpy term, here's your entropy term. Plants need energy from the sun to grow. A continuous input of energy is needed for this reaction to occur. Plants won't grow in the dark. Final example for this. Dissolve ammonium chloride in water. Delta H is positive because the energy is absorbed to break existing ionic bonds, and delta S is also positive. There is an increase in disorder as ions mix with the water. So we have our Gibbs free energy here. At what temperatures will this reaction be thermodynamically favorable? So what do we have? This one's a little tricky. The reaction is favorable only at relatively high temperatures, right here. When the negative term, negative T delta S, is greater than the positive delta H term, then we will have a thermodynamically favorable condition. So we need a big value of T, high temperatures. To make sure you get this, we're going to do a summary exercise. You'll be given the signs for delta H naught and delta S naught, both for the system, and the magnitude of T in the table on the next slide. Give the sign of the change in Gibbs free energy for the system for each of the possible scenarios. If necessary, go back to the table in the section on calculating entropy changes to help you. You can also look at the previous examples. So here's the chart we want you to fill out. You want to calculate the change in Gibbs free energy, and by calculate we just mean plus or minus, okay? So let's start, well, you start and come on back here, pause the video if you'd like, and come back, we'll give the answers. Okay, so let's look at the first one. Delta H system is positive, so let's put a positive right up here. Delta S is negative. Well, what's a negative times a negative? That would be positive. So your change in Gibbs free energy here is always going to be positive. Okay, so let's erase this and then we'll go to the next one. Delta H is positive and delta S is positive. So this term, sorry about that, this term is going to be negative. So what if T is really tiny? Okay, then delta H, the positive will overwhelm the negative, and delta G will be positive. So for small t, delta G is positive. So that's here. What if T is very big? Then the negative part will dominate, and you will have a negative delta G naught. So that will be negative right here. Okay, we'll erase this and go to the next one. Delta H is negative. Delta S is negative. So negative times negative is going to be positive. So if we have a high temperature, this thing here will be very, very much bigger than that. A big positive added to a little negative gives you a positive. And it's nice that it's the inverse of this one here. You'd expect that. And we can go ahead and put a negative here, but I'd rather not. I think we should work through it. So we have a negative delta H. This is positive for the T delta S. If we have a small t, the negative is going to overwhelm the entropy term. So this will in fact be negative like we guessed. Now we go to the last row. And what do we have here? Delta H naught system is negative. Delta S is positive. Positive times a negative, negative. So in all cases, our delta G naught will be negative. And it's also nice that it's the inverse of the one there.